hopefully this will not disappoint. So this is a 2-hour talk. I am incredibly bad at time estimates, so I probably have more material than will fit into 2 hours, but I will just kind of end at a natural endpoint if I run out of time and do another talk another time, which hopefully I'll see many of you at. So the general structure I'm going to try to go for is, so hopefully you've all been to one of convex methods or convex analysis, or at least are vaguely familiar with this. If you're not, sorry. So I'm going to be pretty much kind of assuming you're vaguely familiar with the key ideas and the key results, and trying to talk about like the deeper maths going on, what's the intuition behind the proofs, how to think about the important ideas, like what is a branch car, what is it, come in, hello, you missed nothing, don't worry. Like deeper, so I think about like the deeper ideas, like what is a branch cart, what is a pole, what's really going on here. Oh, sorry, one other thing. This is a diagram which I cannot draw, but is really useful. So I've just printed a bunch of copies. Can people just like pass them around? There's not enough for one each, so just like try and make sure you can see one.
It's so pretty.
But I am deeply not able to draw this diagram. Can everyone see one? If you can't, please just circulate until there's kind of one, but everyone else on that. Cool. So, okay, so I'm going to begin with. Can everyone? Hey, Jack, Tom, Jonty, can people see this board from the back? If we're right down here, is that clear?
For me, but maybe not.
Kyo, where can you see on this board?
Slightly higher.
Here?
Yeah.
Cool. And here?
Yes.
Cool. I will avoid going below this line. That does not leave a lot of space? Oh well. So, yes, but it's the kind of thing where I then have to write down here, and that's a bit useless. And I can't really write up here very well, so I'll just write on a single board, and people can deal. Actually, can people see this? No, that's a bad idea. Sorry, this board is a bad idea, right? Sorry, raise your hand if you would like me to not use this board. Yeah, 3 people. I'll use this one. Okay, so first I'm going to begin with chapter 1, differentiation. I apologise in advance. My hand. I'll try speaking so you can understand this. So
you just dictate to me and I'll write.
You can be my artist if you want.
No.
Also, don't point the talk slow board at me. So, okay, so kind of this chapter is just going to be about like the kind of basic setup and the basic properties of complex functions and complex exponential functions, and trying to like give an intuition and motivation for why they have such nice properties, which I'll then go into a lot more detail about. So the kind of motivating question for this chapter is just like, why is complex analysis so much nicer and deeper than real analysis? So first off, we want to define what it means to be complex exponential. So I'm kind of assuming people have already seen it before. It's the statement that if I take like the change and I divide by the amount I'm changing by, this limits to a constant, no matter what direction I approach it. So I don't really like this definition. So I'm going to rewrite this in a way which I think is a lot more helpful and intuitive. This is equivalent to saying that f of z plus h equals f of z plus h times a constant, f prime of z. Note that I mean a constant as I change h while keeping z fixed, plus little o of h. Have you ever seen little o notation before?
Yeah.
Cool.
Yeah.
So this is like exactly the same as this statement, but I think this is a much more intuitive thing because kind of the heart of differentiation as a topic is I have a function, I'm making a small change near a point, hello, and I want to approximate this change with a nice kind of function, so h times a constant. This is an approximation, so there's a difference, which is an error term, and I say that a function is differentiable if this approximation is a good approximation, which is measured by the error term is like strictly smaller than linear. And so, yeah, so like this is the approximation, and this is the error term. So, first off, observe that this is kind of like the same kind of thing we've been doing in like analysis 2. Sorry, raise your hand if you haven't been to analysis 2. None of the people I care. Cool.
No.
Cool. Raise your hand if you haven't been to Met and Top, otherwise don't know what topology stuff is. Sorry. Cool. So, yeah. So, first property is that complex differential functions are angle preserving or conform. So, like, if I have like a plane like this, and I have, say, two curves like this, and then I square it, so like z maps to z squared, then I get two curves like this, and I measure the angle as a local property, meaning I measure it by the tangent lines, and this is a true statement that if I have any holomorphic function with non-zero derivative, then the angle at z is preserved when I map the curves, and kind of this should be really intuitive from this definition because angles are a local property, meaning I draw tangent lines. So all that matters is what my function looks like locally, and the whole point of being complex differentiable is that locally it looks like multiplication by a complex number. So if I write my complex number as r e to the I theta, then multiplying by this is saying I take h, I map it to e to the I theta times h, I map that to r times e to the I theta times h. This is rotation, which preserves angles. This is scaling, because r is a real number, so it preserves angles. And so it's kind of a trivial statement in a way that holomorphic functions preserve angles. So that's the first nice property. The second kind of property, which is basically a trivial statement, are the Cauchy-Riemann equations. I want to try and convince you that it's actually trivial. So the setup for this is I got a function from r squared to r squared. I can interpret this as like a function fc from c to c, where I just interpret r squared as c in the natural way, like the second coordinate maps to the imaginary part, first coordinate maps to the real part. So all the statements so what I want to do is say, okay, suppose f is real differentiable, as we understand from analysis 2. When is f interpreted as a complex function going to be complex differentiable? So we know from analysis 2 that writing our function as that our function is differentiable at a point x if it looks like so let's say f of xy looks like u of xy and v of xy, like these are the coordinates. Then we know from analysis 2 that the statement it is differentiable just looks like I take this matrix, I multiply the change by this, and I add on something small. So hopefully this line looks quite like this line. Like we're differentiating, meaning we're trying to approximate our function with a certain nice kind of well-behaved function. We want to see when these approximations are the same. And all the Cauchy-Riemann equations are saying is, okay, so clearly our approximation has got to be unique. Like there can't be two different equally good ways to approximate the same function at a point. And multiplication by a complex number is going to be interpreted, something you can interpret as a real matrix. So all the Cauchy-Riemann equations are saying is when is multiplication by a real matrix something you can interpret as multiplied by a complex number? And let's just do a line of algebra to see what this means. So let's say my complex number, the complex number I'm multiplying by is a plus iv. My input is x plus iy. This expands trivially to this thing. And if I interpret this as a linear map, all this is saying is I take in xy, and I get out ax minus by, bx plus ay. And I hope it's pretty clear what these coefficients need to be. This needs to be a, this needs to be minus b, this needs to be b, this needs to be a. And so what we get are the Cauchy-Riemann equations. So this matrix can be interpreted as multiplied by a complex number if and only if ux equals vy and vx equals minus uy. And this is all the Cauchy-Riemann equations are saying. Like, there's no, the proof should be this easy. It's just, can you interpret a 2 by 2 real matrix as multiplied by a complex number? Another important thing to note while we're on the topic of real differentiation versus complex differentiation is that, like, the map we're choosing to approximate by is a different kind of map here. Like, there are 4 real degrees of freedom in here, and there are 2 real degrees of freedom in here. Like, what is the complex number we're multiplying by? The significance of this is that saying something is complex differentiable is a much, much stronger condition than saying it's real differentiable. And so the heart of why the subject is so nice and why it has so many nice properties is that we're insisting on having this much stronger condition. So I'm now going to talk about kind of what our intuition should be about why this is so nice. Does anyone have any questions about this before I brought it out? No? Excellent. So why are complex differential functions so nice? So I think kind of the key thing here is that the way we've defined a complex number, if I have a point and I know what the function looks like on a line through that point, meaning I know what it looks like as it approaches from one direction, I know what it looks like as I approach from any direction. This is not completely obvious if the derivative happens to be 0 at this point, but as we will later show, complex differentiable functions are power series locally, which means they look like a constant times z to the k locally, which means, and if I know what it looks like on a line, I can figure out what this k and what this coefficient are. I'm currently trying to give you an intuition, so don't worry about the fact that we have completely not proved that. All this is saying is that if I know what my function looks like on a line, then I know what my function looks like a little bit off the line. Like, I can take a kind of tiny disk, and I have an idea what the function looks like on that disk, because of how we define complex differentiation. And this means that the same is true for any point on this line, which means I can just take lots of little disks, and I get a kind of 2D fuzz around my original line, and I now understand how my function works on this fuzzy 2D region. And I can just keep doing this. Again, this is like an intuition. So if your mind is screaming at you, oh, how do you know it converges? How do you know you don't just keep getting a limit of things converging to some boundary? That's a completely bad thing to be concerned about, and we're going to prove all this properly later on. But for now, I just want your intuition to be, if we know what it's like on a line, we can kind of just expand outwards. And another deep and important thing to note is that continuing this intuitive picture, if there's a hole in our domain, like a point where our function is not defined, and we kind of try to fuzz out around this hole, what we end up getting is we kind of have an idea what it looks like over here. We have an idea what it looks like over here, and these two regions can meet, but it's not actually determined that they are going to be the same, because they've been split in two, and we'd hope they'd be the same, but there's not actually a kind of deep canonical reason this must be the case. And indeed, if we look at functions like log of z, or things with branch cards, it's not the case that they're the same. And, well, I hope I've kind of given you some intuition for why this should be so nice, and why our condition is actually so strong. And as I'm sure you already know from the course, we're going to get loads of really nice results from this. Like, on any space with no holes in it, there's an antiderivative. If it's differentiable once, it's differentiable infinitely many times. We can look at it like a power series. If it's bounded on the entire plane, it is constant. So, a kind of natural question to then ask is, okay, so this condition is really strong, but so is assuming your functions are constant everywhere. Why should we care about the topic of maths at all? This isn't really the point of my talk, because I'm a pure mathematician, not an applied mathematician, but as a nod to those people, I think the strongest arguments to this are that, like, the real numbers live inside the complex numbers, and so understanding how functions can behave nice on complex numbers tells you a lot about how they behave on the real numbers, which we already care about. Like, this is the entire point of the complex methods course, for example. How to do hard integrals using these ideas. And as we will see later on in the talk, there's some really cool and deep links to how topologies and spaces work. Like, as you would have seen at the end of complex analysis, we can use these tools like integration to study how curves wind around spaces. How curves wind around holes, and what is the topology of our space. And these turn out to be really powerful tools to kind of formalize intuitive things that are really hard to work with. And there's also some application of vector calculus, but who cares about those? So, just gonna grab a drink. So, now I want to talk about our branch cuts, and kind of what's really going on when we have a branch cut. So, hopefully you're kind of familiar with the idea of a branch cut. Like, we have a function like, say, log z. And so log z would define, we want it to be the inverse of e to the z. But when we try and actually define this, we run into issues. And the reason we run into issues is that if we look at the complex plane and think about how e to the z maps things, then if we look at this axis and mark points at 0, 2 pi I, 4 pi I, etc., then they're going to map to the unit circle. But now all of our crosses map here. And so this should be our, this is kind of the first time where the fact that we're in 2 dimensions rather than 1 dimension becomes really important. We want to invert a function. We're struggling to do this because it's a one-to-many function. It's a many-to-one function. And so our inverse is going to be a multi-valued function. That's really weird. In the real numbers, we do sometimes have functions like this. For example, x squared. But the only time you get a function that looks like that, that's continuous, is when it doubles back on itself. If we look at x squared between -1 and 1, and we map it, then it kind of bends around on itself. So if you trace it along the line, it doubles back on itself. There's a point where the derivative is 0. And you kind of note this in real analysis as, we can't take an inverse here because the derivative is 0, but we just kind of look on either side of this. And that's totally fine. But here in the complex plane, because things are 2-dimensional, we aren't forced to double back on ourselves if we want to repeat. We can just go in a loop, and indeed that's what happens. And as we will later see, this behavior, which seems kind of weird and annoying and non-canonical, is actually give us a really deep way to understand important things of our space, like how many holes are there, how many times does a curve wind around a hole. So, okay, that's enough rambling about branch cuts on a very high level. Let's think about what actually happens when we try to define this inverse. So, we want to define log. So we want to take something from this plane and go back. And we know that the exponential takes on every value apart from the origin, because the origin is like annoying and weird. And so what we want to do is look at this point, it's 1, and we want to try and take like a pre-image of this. So we're already running into issues because we'd love to just say there's a sensible canonical inverse, but we want to make a choice here. But let's make a choice and see what happens. We map it to 0, and now we just like kind of look a little bit around us, and 1 gets quite nicely mapped. Sorry, the area around 1 gets very nicely mapped to the area around 0. So it looks like things are going well. But then we kind of extend our way around, and we've kind of gone in a loop, but over here we've gone in not a loop. This seems wrong. And so the standard way and so kind of what's really going wrong here is we've got this annoying hole in our space, and when we've got a loop around that hole, stuff breaks. So the way you deal with this in kind of complex analysis and complex methods is you just say, I'm not going to allow myself to go on a loop around a hole. I'm going to just draw a line, call it a branch cut, ignore what's happening, and ignore how cool it is, and just say, this thing that breaks math is not allowed, so everything's good. But, yeah?
Why is that hole that important?
Getting to that. So, the reason... Okay, so... Yeah, so in general in maths, when you have something where you make arbitrary choices, like, what is my branch cut? What does 1 invert to? And no matter what these arbitrary choices are, you get some like cool and deep structure. Your intuition should be telling you there's some deeper maths here that I just don't understand. And all my arbitrary choices are doing is giving me a way to access this deeper maths. Like, for example, when you're doing linear algebra and you're choosing your coordinate axes, no matter what axes you choose, you still get a way to interpret the same underlying space. And when you're doing a vector matrices course, you might be like, this seems weird, but all that's happening is there's this underlying geometry of points in space, and the axes you choose are a way to interpret this. And a similar but much harder thing is going on here. So now is a great time to look at the picture I handed out earlier. So the idea is, okay, so I started at 1, I inverted to 0, I now kind of explored outwards, and it looked like I had a really nice, well-defined inverse. But then, when I got back here, I realized I was at a different point. And indeed, everywhere along this line, I started as kind of, I started as a real number. When I got back, I was that real number plus 2 pi r. So we could just draw a line here and say we don't want to do this. But why not just say, okay, I'm just going to invent some new points. I'm going to see what happens. Clearly, I've got a well-defined, clearly something cool is going on because I'm getting this like clear, sensible inverse. But let's just invent some new points and say that I'm going to keep going in this new space. So geometrically, it's kind of like I've taken the complex plane and I've ripped it. So the picture you should have in your mind should hopefully look something like this. Like, I've kind of ripped this bit up, and I've like taken the other part and kind of ripped it downwards. And now it doesn't look like there's a contradiction. It just looks like I've just gone to some different points. And I could take another copy of the complex plane, send 1 to 2 pi I, and just kind of continue onwards. And I could solve this problem by just taking like countably many complex planes, and then on each one taking the same branch cut, but mapping one to a different thing, and just interpreting from that point outwards. And then I could just glue them all together and say, this is sensible. Or I could say, okay, so I've done all that. I've glued together along this axis, but there's nothing special about that axis. And indeed, if I like cut along here and glue along there, it's the same thing. So what's really going on is we're kind of taking an infinite stack of complex planes and just like ripping each one and gluing it to the one below and getting a spiral, as should be on the image you have in front of you. And so this is like, this is not just a mathematical curiosity. This is what's actually going on when you have this branch cut. Like in part 2 Riemann surfaces, you will do this kind of thing to death. But the core idea is just, okay, so I have this function, it's e to the z. It looks like it's many to 1. But if I instead map it onto this complex spiral, where I just have like stuck lots of complex planes together, and this means that rather than kind of bending into a circle, the imaginary arc just bends into a spiral. And now it's still 1 to 1. And because it's 1 to 1, I can just define an inverse. And so everything you're doing when you're taking a branch cut is just saying, okay, so I've got this like weird spiral. I'm not going to try and draw this because that always goes badly. And you're just taking like a slice out of the spiral and saying, this looks like the complex plane. So I can just look at what my functions like here. But I think it's very important to bear in mind that there is this deep underlying object. And the same is true for other many to one functions. Like, if you take z squared, we again get the same problem. Like, 1 could invert to 1 or minus 1. And then when I can generate like a sensible square root from either of those. But when I wind around the origin, I end up with another one, at the other one. Square roots are a little bit different because when I go around twice, I end up at the same point. But you can think of this as taking 2 complex planes, ripping them, and then saying, okay, now I'm just going to like glue this bit to the top and glue this bit here. So I'm basically taking my infinite spiral of logs and just taking it mod 2. I think this is like quite hard to visualize, so how well are people following? Like, raise your hand if this is confusing you greatly. Raise your hand if this is not confusing you greatly. Excellent. Way better than I expected. Okay, cool. So, yeah, that's like what you should have in mind when you're doing branch cuts. And as you will see in a bit, this is actually kind of a really, really important surface when you're doing this kind of thing. So, okay, so that was the end of chapter 1. To recap what we've just done, we talked about how we're defining complex differentiation as just approximating by multiplying by a complex number, and how the definition is just saying this is a good approximation. We get the easy consequence from this, that it preserves angles, because locally it's just rotation and enlargement, and the Cauchy-Riemann equations are just saying, okay, so a function is differentiable over r squared if it can be approximated by a real linear map. The Cauchy-Riemann equations just say, when is this linear map something that looks like multiplication by a complex number? We talked about how the condition is so strong that it tells us, if we know what looks like in any direction, we know what it looks like in every direction. And this is kind of why the structure is so nice. And we talked about how branch cuts are kind of bullshit. All branch cuts are doing is telling us that this deep underlying structure of this cool spiral. And we're just taking slices and thinking about them in a way we're comfortable with. I think now's a good time for a very short break. So if anyone has any questions, that'll be a great time. That seems like no questions. So I'm going to have a drink and stare at you. Yeah.
How many like different types of surfaces can you make with one branch cut? Are there, if you make a complicated enough surface, do you have like a really, really complicated Riemann surface, or is there just like only a few Riemann surfaces? Is it only like the log spiral and then things that look kind of like?
So the only one chat. Also, now's probably a good time to check. It's kind of the pace okay? Should I speed up, slow down? This good? Nice. That's way better than I expected this to be. I've not given a talk in like several years. Okay, so chapter 2. I'm gonna kind of talk about what we're really doing when we do complex integration on a high level. This is not going to be a chapter about proving results. That's all in chapter 3. Now I want to just kind of talk about what the point of complex integration is. Like, why do we do it? Where did the definition come from? Why is it so much weirder and more interesting than the real case? And why do we get such like random results, like the integral along the loop is 0, but if there's a hole in the middle, the integral can be non-zero. Like what? Okay, so the most basic question here is just like, why is integration so much deeper and harder in the complex case than the real case? And I think a very good example to bear in mind throughout is that the integral along a curve of 1 over z is kind of the change in angle as you go around this curve. So over a closed curve, it's n times the times one around the origin. If it's not on a closed curve, if you've been to the course, you know what it is. If you haven't, then don't worry about it. But I think like, this is a very good example to keep in mind throughout, because this kind of captures the essence of all of the weirdness of what I'm about to talk about. So if you're ever confused and want to put things in context, think about this. So, okay, so the central question that we're trying to answer when we define contour integrals is, I have a holomorphic function. Does there exist an antiderivative? So it might be the case that antiderivatives don't exist at all, in which case trying to construct one's going to fail, because there isn't one. But let's kind of be optimists. We hope that there exists an antiderivative. How could we try and find it? So the way we can try and find an antiderivative is say, okay, so I can subtract a constant, and that doesn't affect whether it's antiderivative. So I can just fix a certain point to be 0. Call this the base point, b. And I want to figure out what my antiderivative looks like at another point, z. Then I know the change at each point in space, and I want to go from that kind of local property of the change at each point to the global how much total change has there been. I don't think that was a course where I thought really hard about how to do this. Oh wait, there was. So we can just pick any path between b and z and say, okay, at each point on this path, the change is my function. And I want to just iterate along this path in order to find out the total change. Path is like a function gamma from the unit interval into c. And I'm going to try and define my antiderivative. I'm going to call this g, so I don't say f and f all the time. I don't know why that connection exists. This is the... I want to have notation that means this. And so what I actually write is I'm going to kind of move along my path, and then at each point in the path, the amount I change by is the gradient of the path, like the kind of amount of change per unit change as I move within the unit interval, times the kind of constant coefficient of how I'm changing at that point. And this is exactly the definition of contour integration. This is approximating what a change looks like at a small point. This is the change in the input, and this is the scaling factor to find the change in the output. And real integrals are a tool to say, I know how something changes at each point along a real line. What is the total change? And kind of all of the results we understand from real analysis, we can just kind of import into here, because we understand how things like this work. It's slightly weirder because this is a function from R into C, but if you want to formalize this, you can just say, look at the real parts, that's normal, look at the imaginary part, that's normal. This isn't interesting, so I'm going to assume everything works. If that bothers you, sorry. So, okay, so the heart of like everything that is deep and weird and cool about complex analysis is that we have so much freedom in what path we choose. We're in 2 dimensions. If we're in 1 dimension, there's only really one path, it's just the line, or maybe a line double back, but kind of doubling back obviously does nothing, because we're adding up changes. So this problem never came up in real analysis. But here we're in 2 dimensions, but we only care about this 1-dimensional thing. So we can just kind of move it around wherever, and it's completely not obvious at the start that this is actually going to give you the thing you want. And indeed, if there isn't an antiderivative, then there's no reason this should. But let's kind of sanity check. Let's suppose there is an antiderivative. Like, there exists an h from C to C such that the derivative of h is our function. Then, what this thing looks like is the integral from 0 to 1 of this. And, oh look, I can integrate by substitution. This is just the derivative of h composed with gamma. So this is just the difference between h at both ends of the curve. And like we've just constructed h up to a constant. This is great. So kind of it doesn't really, under the assumption that there exists an antiderivative, we've just found it. This is great. This is amazing. And this kind of completely solves our problem of how path dependent this tool is. Because if there's an antiderivative, what we've just shown is it doesn't matter what the path between the 2 points of space is. All that matters is the endpoints. Of course, the assumption there exists an antiderivative is slightly dodgy to make when we're trying to construct them. So we can't rely on this when we're actually trying to do things. But let's think about how we actually study how path dependent something is. So the best way to study this is to say, okay, I've got 2 different paths between my 2 points, like gamma 1, gamma 2. I want to look at whether the integral is equal along these 2 paths, also known as is the difference 0. But the difference of the integral along gamma 1 and the integral along gamma 2 is the integral we go along gamma 2 and then back down gamma 1. So the statement of is our tool an effective way to construct an antiderivative is really just a statement about what are integrals around loops 0. And so every theorem with Cauchy in the name is basically just saying how effective is my tool. Like convex Cauchy is just saying this works in convex domains. Something against Cauchy is just saying this works in domains without holes in them. So yeah, unfortunately, it is not actually true in general that the integral around a loop is 0. As you know, if you're paying attention to our most basic example. So let's think about what actually happens. So I'm going to assert a fact which might annoy some of you. Fact: if I can deform gamma 1 to gamma 2, like as parts, the integral is the same. This is just Cauchy's theorem. We're going to prove this later, but I think it's quite helpful to just assume it's true at the start and think about the consequences, and just bear this in mind while we're actually doing this all later on. So, first off, I'm guessing people aren't super familiar with what it really means to deform one path to the other. You'll do this to death in algebraic topology, an excellent course, but it's a great course. So go to that if you really care. But kind of, the statement is what the statement is saying informally is that like if I have 2 curves, I can kind of like smoothly vary one to the other. Like I can just draw lots of partial curves to get from this to this, while keeping the endpoints the same. And the point of this is that the statement I can deform one curve to the other is another way of saying there is not a hole between them. So from henceforth, I'm going to try and phrase this all in terms of holes, because as you know from things like residue theorem and singularities, when a holomorphic function is not defined is really important. And this is just because if there is a hole between these 2 curves, between these 2 paths, we don't actually know that the integral along them is the same. And indeed, sometimes it's not. So, yeah. Okay. And, okay, so let's kind of ignore this problem for a moment. Let's say we did show that the integral is path independent. This is kind of what we're trying to show, so we should be happy. We should check that we're actually happy. So, first off, we now have a well-defined thing that we would like to be an antiderivative. I can define g of z as, so assume path indep. Now I have a well-defined thing, which is just a path from B to Z, and the whole point of being path independent is that this is now a well-defined function. It doesn't matter what this path is. Note that if Z is B, I can just define this to be 0, so we don't worry about things like what it means to have a path from itself to itself. So, okay, if there's an antiderivative, you're probably familiar with this, but the core idea is essentially just I have a point Z plus H, I have a point Z, I take I've got my base point B, and I take G of Z plus H minus G of Z. And we kind of saw earlier, when you have the difference between the integral along the curve, the integral along the tube curve starting from the same point, that's just the integral between the 2 points via the base point, but it's path independent. So we can just take the integral along this line, and now we're basically done. We've got the integral along a straight line of a continuous function, f of z plus thing even smaller than h. And I'm not going to formalize this, but it's kind of a very easy exercise analysis to show from there that the integral of a thing which is approximately f of z along a curve of length h is h times f of z. So if we do have path independence, we're really happy. So now I'm going to remove this assumption. And let's think about the implications of the statement. If there are no holes between two paths, then the integral is the same. If it is actually the case that the integral, if there is a hole between them, the integral is different, then this is now a really cool tool, because we can translate topological statements, like there's a hole in our space, or there's a hole inside our loop, into just an algebraic statement, or an analytical statement. The integral around this loop is not 0. And that's incredibly cool, as we'll see later on. But let's kind of break things up into cases, depending on what the topology of our space is. So case 1 is kind of the boring but useful case. There are no holes, i.e. simply connected. I'm lazy, so I'm just going to SC for simply connected. We kind of, from the facts which I'm going to prove later, we know that it's path independent because all paths can be deformed to each other. That's kind of what simply connected means. So in the case if we have an antiderivative, we're really happy. Where things get cool and weird is case 2. So there is a single hole. This is where the example of 1 over z becomes really key, because 1 over z has a single hole. I think this might be hard to visualize for some people, so if you don't follow this, don't worry. I'll just say when you can start paying attention again. But try and follow this is cool. So if you'll again refer to a fabulous diagram, I'm not going to try drawing again. So a deep result from algebraic topology is that if you have a space with a single hole in it, and you're trying to figure out whether one path can be deformed to another, all that matters is the number of times they wind around this hole. There's a lot of deep theory behind how you prove this, and kind of intuitively the idea is to project onto a circle and kind of smooth out the curve into the number of times into just winding around at uniform speed, and proving that if something winds around once, you can't deform it, so if it winds around no times is hard, but I hope that's intuitive, that people take it on faith. So kind of all that so we say that two paths are the same if they wind around the same number of times, and different if they wind around a different number of times. So rather than thinking of my antiderivative as taking as an input the endpoint of the path, I could instead think of it as taking as an input the path and all paths that could be deformed to it. Or equivalently, it could take as an input the endpoint of the path and the number of times it winds round. Another way to think about this is, for every different way of getting to a point in space, I make a different copy of that. So let's think about what this would look like. I start here, I kind of explore outwards, there's one way to reach everything, and But when I get back here, I found a new way to reach the start point. Originally it was just doing nothing, but I found a way to go around the origin. So I'm just going to say this is a new point, and I hope this is sounding familiar to people. All I'm doing now is I'm kind of, again, taking complex planes and kind of gluing them together, ripping them and then gluing different sheets together. And so the people who know any algebraic topology, what we just constructed is a universal cover. If you don't know algebraic topology, don't worry about what that means. But the idea is essentially, I want to construct a space where at every point it locally looks like my original space, but I've removed the ability to wind around like the origin and get back to where I started. I.e., I've removed the ability to have more than one path from the same point that looks different, that kind of can't be deformed too much. So let's think about why this has happened. Like, over here I had a loop, and this couldn't be deformed to the do nothing part. But over here, it looked like kind of, I start here, I wind around, and now I'm kind of on a new sheet. Or, that example is probably not very helpful. I start here, I wind around, I go on to the sheet below, and now I've kind of ended up on a different level. So what looked like a closed curve in the complex plane is not a closed curve on this surface. And it turns out that this kind of weird spiral we've made is simply connected. And so all of the kind of deep results we had earlier about there is an antiderivative that's simply connected kind of apply here. It doesn't look like the complex plane, but that doesn't matter. All of our theory still works because at each point it looks like the complex plane. And there's also, as a kind of fun bonus, gets us that the winding number gets us the winding number. So the only thing that matters about a curve is the number of times it winds around the origin. Where when I say matter, what I mean is the only thing that determines whether you can deform one curve to the other is the number of times it winds around the origin. Now, when I kind of lift it to this spiral, winding around the origin instead becomes go up one sheet. And so it's kind of obvious that winding around the origin, the number of times around the origin is important because that's the number of sheets I've gone up. And that feels like a natural thing I should be able to figure out. And so the whole reason you get things like winding number is just that you're saying, okay, so I'm integrating around this spiral, and the length of the spiral is the number of times I've wound around. So it's kind of natural you'd get things like winding number. And it's also worth kind of being explicit about why we've just ended up with the same image we had when I was talking about branch cards and constructing inverses. So block can be thought of as the inverse of e to the z, but it can also be thought of as the antiderivative of 1 over z. These are kind of equivalent ways to define the same thing. Defining an antiderivative has given us this like natural spiral where we say that winding around the origin puts us at a different point. Defining the inverse of e to the z has also given us the same key idea. And it's not a coincidence, like these two different roots gave us the same function, so obviously they give us the same image. Cool, so that's the end of the like hard to visualize weird bit, so please do following if you got lost during that. I think that was potentially confusing, so if anyone has any questions, now's an excellent time. Yeah?
Is it possible for a function to have a genuine hole, but also have the property that if you integrate around that hole, you still end up with 0 regardless of the winding
Yes.
number?
So if you recall earlier, we said that if there is an antiderivative, it is path independent. But we didn't make any assumptions about like being simply connected or path deformation. that just follows from the fundamental theorem of calculus. So it's completely independent of the topology of our space. So if you just pick any function which has an antiderivative, no matter how many holes or how many singularities or whatever weird crap's going on, it's still going to be the case that any integral around a closed curve is 0. For example, that's why if you look at the integral of like z to the minus k around the origin, it's 0 if k is not equal to 1. Because the antiderivative of z to the minus k is z to the 1 minus k over 1 minus k, probably. That sounds like A level, I don't care about A levels. And it's actually a true result that if you like integrate around the like unit circle, z to the m for m an integer, this is 0 if m not equal to minus 1, and 2 pi I if m equals minus 1. People have, I hope, seen this result before, but hopefully it kind of makes a little bit more sense now. Like, 1 over z is the only one of these where trying to write down the antiderivative gets weird. And the reason trying to write down the antiderivative gets weird is the antiderivative of 1 over z is log, and log is an inverse, and inverting functions is a lot harder in 2 dimensions because you can get kind of discrete one-to-many functions. Like you can have a path which eventually gets back on itself without doubling back. While all of the other things, the antiderivatives are just polynomials, or like 1 over a power of z. These are still well-defined things. Cool. Any other questions? So, cool. So, what I could do now is just like start to say case 3, 2 holes, case 4, 3 holes, etc., and I could be here all night. But as we'll later see, this doesn't actually, none of these cases actually matter, because so having a hole in our space is having a singularity, and as people have hopefully seen, whenever you have a singularity, like a singularity at 1, for example, you can write f of z as like a holomorphic function of the z minus 1 plus a holomorphic function of z, which no longer has a singularity at 1. And so this is just like the weird terms in the Laurent series. If you don't know what the Laurent series is, I will explain to it later if I get to that, which I really won't. And if you and we can define G as a function with a singularity at 1, but is holomorphic everywhere else. And so from G's perspective, the topology of the plane is just there is a single hole. And from H's perspective, there is like 1 fewer holes. And we can just like keep doing this for every singularity. Like, say there's 3 singularities at 1, 2, and 3. Then we can get like we can just get this, which thinks the plane has a single hole in it. This, which thinks the plane has a single hole at a different point. This, which thinks the plane has a single hole at a different point. And this, which is holomorphic and boring. So we don't actually ever need to care about more complicated topologies like multiple holes, because we can break this up into different bits, use the fact that they add together to look at each bit in isolation, and in each bit we just get one of the 2 cases we've just studied. And yeah. And again, if you thought this kind of thing was cool and you want a like actual approach to this rather than some intuitive hand waving, go to 30 Riemann surfaces or algebraic topology. Or ask me, but that's less fun. Yeah, so kind of just to recap everything we've just found, we tried to construct an antiderivative. This required it to be path independent. We tried really hard to hope it would be path independent, and it was kind of path independent, but not completely. And this ought to have kind of just killed the entire project, but it turned out that it was path dependent in a really cool and interesting way that meant that if we look at a different surface, it is path independent. We were just looking at the wrong thing. And I kind of hope it'll be a bit of a theme in this talk, that whenever things get weird, it's just a sign that you're looking at the wrong surface. And it turns out that this tool for constructing antiderivative is actually more powerful than it would have been if it was just path independent, because this lets us access deep topological properties, like how many times it went around a point, which, as we will see in the chapter I definitely won't have time for, is really cool. So, yeah. That is the end of chapter 2. Take a short break. Any questions? Just check again. Good pace, too slow, too fast, people following? Anything people? Stop the break, I'm sitting down,
Yeah.
that's good.
Neil,
Yeah.
for audio syncing help later, do you mind just clapping for me? Thank you.
You're putting us up.
Yeah, I hope you guys are all cool with the 2-hour talk, by the way. Yeah. I'm not running out of steam. Also, the room's also available after this. Okay, so chapter 3. So now I'm gonna stop just talking about woolly fuzzy intuition and actually prove things. So this chapter is convex Cauchy and power series. And the motivating question for this section is basically, we've kind of got this clever idea of contour integrals, and we hope it makes an antiderivative, but I clearly gloss over any of the actual proof there. So we want to try to figure out why things work. So this is the section which I think is going to be closest to the stuff you've actually done in the course. So basically going to just give a bunch of theorems and prove them. But I'm going to try and focus on the intuition rather than the details. Like, why would you expect this theorem to be true? What's going on behind the proof? Like, how could you kind of mentally summarize the proof to a few bullet points rather than just write down a bunch of rigor and memorize it? And hopefully you guys are cool with this. If you're not, please leave. Okay, so first off, we know nothing, but we've got this idea of taking paths and taking integrals on the paths. We want to solve the problem of there are many paths, maybe it's path dependent. So the easy way to solve this problem is to say, pick a single path. And what's the easy way to pick a path between 2 points? Any takers? Yes.
Straight line.
Yes! Have a good. So you chop this around, give Michael one.
Yes.
Have a prize.
Hey!
See me this up on by order of practice. Sorry?
Are there more?
You can have whatever's left from Michael's.
Fine, you can share.
So the first thing I'm going to try and do is say, rather than looking at all possible paths, I'm going to just look at a single canonical path, so the straight line. So the first thing to observe is that it's not always true that I can draw a straight line between 2 points. So I'm just going to only study convex sets, because then I can do this. You might have done star-shaped sets in convex analysis, but I have never seen a star-shaped set that wasn't also convex. So I was going to say convex because it's shorter. Okay, so we're trying to study, so we're going to construct our antiderivative by defining gamma z as the straight line path between our base point and z. So this is just a straight line between b and z, which are complex numbers. And I want to define an antiderivative on my convex region with a base point of b as big G of z is the integral along this path of my function. So this is now a fully well-defined thing. I've removed all my issues about path independence by just saying I'm going to forget about caring about all possible paths. I'm only going to care about this. And remember that my overriding goal is constructing an antiderivative. I don't really care about what the integral along a weird wiggly path is. So it's perfectly reasonable to just forget about it and say I'm going to take a single path. This also loses me some of the nice properties, which let me prove cool things, but I'm going to get to that eventually. So let's think about what it would mean if there's been antiderivative for this function. So hopefully this is quite familiar to people. I just want to try and repeat the proof I had last time of path independence implies integral 0. So, implies antiderivative. At point z, I have a nearby point z plus h. I take the difference between the value of those 2 points. This is the integral along this like V-shaped contour, and what I really want to say is this is path independent. So the same as along the line along here, and with the line along there, I'm just done. Annoyingly, I need to prove this because I'm doing actual proofs now. But this is a much simpler statement than it's path independent. All I'm doing is saying if there is a triangle, I am happy. And you can kind of reframe the result I use for this to be true as the integral around a triangle is 0. So let's prove this. So theorem, Cauchy's for triangles. Triangle's a long word. So I define T a triangle, meaning like the region of space, like the kind of interior but also the boundary. I'll write the curve as like delta t to denote like the curve around the boundary, and f hollow on t, or actually f is hollow on like an open set that happens to contain t. The reason I need it to be an open set is that being holomorphic is only really well defined when I can approach from any direction, and T is closed and bounded. Like, there are sides to it. I need to assume that it's holomorphic on an open set, so that I can just look at any point and just approach from any direction. The reason you will see the phrase open, or possibly domain, in basically every single statement in complex analysis is that open is just another way of saying the set does not contain its boundary, and holomorphic is well defined unless you're on a boundary point. So it's just saying, ignore that case by just defining a way out of it. And closed is the converse of just it contains its entire boundary. Which also has the fun corollary that clopen actually makes sense, and just saying the set that both contains all of and none of its boundary, or a set with no boundary, rather than a living contradiction. So we're trying to do Cauchy's for triangles. So I think this is probably one of the hardest proofs in the entire course. So I'm going to try and talk for a while about why we'd expect this to be true and why it's a hard proof before I actually do anything. So, let's suppose we're working with let's suppose we're working in a really easy, simple case. F linear. So F is linear implies antiderivative, which implies integral equals 0. So F, unfortunately, is not going to be linear in general, but F is going to be locally approximately linear. So I'm just going to write this word here. And there. And so it's locally approximately linear. This is just what being a holomorphic means. Like, if I zoom in really far, it looks like a linear function. So that means it's locally approximately got an antiderivative, because all linear functions have antiderivatives. They're just polynomials. We understand how polynomials work. So locally, approximately, writing is hard. And it's locally approximately got an antiderivative, which means that if I have an integral on like a really small curve, like a curve in a really small region of space, it's going to be approximately 0, because most of the function is antiderivative. And I can split this into integral of antiderivative plus integral of error term, and we already know the integral around a closed curve of an antiderivative is 0. So kind of the integral on small things is approximately equal to 0. Like, I'm just trying to give an intuition right now, nothing rigorous. But basically the entire proof is just formalizing this idea. We split the triangle up into small triangles. On each triangle, it's approximately linear, so it's approximately got an antiderivative, and that bit just vanishes when you integrate. So all we're doing is integrating error terms around lots of small triangles. And the meat of the proof, well, not the meat, but like the fiddly details of the proof are just showing that those error terms aren't big enough to matter. And the statement of is convex differentiable is a statement about how big the error terms are. And they'll turn out to be the exact thing you need to get them to vanish. So, okay, so let's think about how we break our triangle up into like small things to integrate around. So let's draw a bigger triangle. And let's say I'm going around anti-clockwise, because I like going anti-clockwise. So like, this is my big triangle T. I now want to split it up into smaller triangles. Like, one of the reasons triangles are really cool is that triangles are like a nice geometric thing. And so I can do things like split them up, because they're really lovely, I can shrink them, they tessellate nicely. So I'm going to split this into 4 smaller triangles, and then I'm going to just like define an orientation on each smaller triangle. And now, like, I can take the integral around the smaller triangles, add them all together, and get the integral around the original triangle. Hopefully this is pretty familiar to people. Each of these lines cancels with each other. And I now am going to start every triangle again, and again, and again, and I'm going to get like an infinite, like, 2 to the n triangles after doing this n times. 4 to the n triangles. And so what I'm really trying to show is that on each of these triangles, they are small. F is like basically linear on a small region. So F basically has an antiderivative on a small region. And so the integral of F is basically 0 on a small region. If I can show that the error terms integrate to something smaller than 1 over 4 to the n, I'm now just done. So that hopefully made intuitive sense to people. There are 2 reasons this is hard. The first reason is many triangles. It's not enough to just say the integral around a triangle goes to 0. I need to think about the rate that it goes to 0. And I need to think about the rate that it goes to 0 across every triangle. And if you've done any analysis, you know that thinking about rates across many things is much, much harder than thinking about rates for a single thing. I can't just say there exists an n such that things work. I need results like uniformity and hard stuff like that. And the second reason it's true is that this requires me to go from a local property to a global property. Let's think about what I actually mean by that. So local properties are statements which are true on like an arbitrarily small region of space. Like, this function is differentiable. This function is locally bounded. This function is like locally constant. This function is a local maximum. This function is holomorphic. And a global statement is more like a statement about like the actual space, like things that are some finite distance apart. Like, what is, for example, what is the integral around a triangle? And a lot of the really hard bits in analysis proofs are that we have a statement whose conditions are local things, we have a statement whose conclusions are global things, and we need to do something clever to go from local to global, because our intuition isn't very helpful on this front. Indeed, that's the reason that like half the theorems in analysis 2 basically use the mean value theorem in a clever way, because that's like a really powerful tool to go from a local statement, differentiability, to a global statement. There is a point with a certain gradient. I highly recommend reading through analysis 2 and trying to highlight where the mean value things used in each proof. It's a really effective way to just learn the entire course. Okay, so let's think about how we solve these problems. So first off, many triangles. This is really annoying, but I know that if the integral around the big triangle is like I, some actual number, then the integral around one of the small triangles is at least I over 4. So I can just look at this maximal triangle. Say it's this one. Then there are 4 triangles in there. One of them has integral at least I over 16. I can look at that triangle. I can just keep doing this. And I get a like nested sequence of triangles. This has solved this problem, because as long as I can show that the integral around these chain of maximal triangles shrinks faster than 4 to the n, I am done. I've reduced many triangles to like a single chain. So yay, this is massive progress. And now I'm going to cite a result from Metentop. Each triangle is a closed and bounded region in complex numbers. So it's a compact set. and we know that we've got a nested chain of compact sets. There is a point that lies in all of them. If I'm met on top, this is a fact. Accept it. So there is like a single point inside all of them, and do the triangles shrink? Like it must be a single point. And we wanted a point to look at. Maybe we should look at the spot. So the way we bridge the kind of local to global thing is we look at that point. We know a statement about the rate of like how good linear approximations are to that function, like around that point. And now we can just look at the nested chain of triangles and say, okay, so I know that f of, like, say that point is A. I know that f of z is f of a plus z minus a f prime of a plus something small in terms of z minus a. And this, like, little o of z minus a thing is just kind of how small it gets as you zoom in on that point. So the kind of hard part of this theorem basically just reduces to saying, okay, so I want to integrate f of z around like a tiny triangle, Tn, and so I'm integrating a constant plus a linear thing plus something strictly smaller than linear. And these both have antiderivatives, so they vanish. So we now have, and now we can just apply like the standard bound to integrals. We have the length of this triangle, which is kind of some constant over 2 to the n, because length shrinks with 2 to the n. We've got this bit. This is a, z minus a is a length within the triangle. The biggest length within the triangle is like something, it's a constant, and it's going to shrink with speed like 2 to the n. Another constant over 2 to the n. But it's like strictly smaller than that. That's what this alone is. So like something which is like strictly worse than 1. And what I want to show is that this shrank faster than 4 to the n. We have done this. So we're now done. Like, all of the random algebraic crap you do when you're proving this is really just kind of formalizing all of these ideas and writing down on paper. Cool. So that completes the hardest proof of this talk. Any questions? Did I make more sense than what Kovalev did? Nice! My job here is done. Yes?
Can you repeat the Latin top thing?
If you have a nested sequence of compact sets,
Okay.
so stuff that is closed and bounded and R to the n,
Yeah.
then there is a point that lies in the intersection of all of them. Prove that next time. I expect you to have solved next time. Okay, so that's cohesive triangles, and now we're just. Yep, sorry.
When you said it has to be holomorphic on an open set containing the triangle, does that mean like the entire triangle and its interior?
Yes, I define the triangle as interior plus boundary.
Oh.
Yes.
Could you remind me, because I missed it, how did you generate the sequence of nested triangles?
You look at, so you know that the sum of the 4 triangles is the original, the sum of the integral around the 4 triangles is the integral around the big thing. So one of them has, you pick the triangle with the biggest integral. This has size at least original integral divided by 4. You then recurse on that triangle, you pick the biggest subtriangle, repeat. And this is key because it tells you that the integral shrinks at rate 1 over 4 to the n.
So what's the statement of the theorem again?
If you have a triangle and a holomorphic function that's defined on this entire triangle, then the integral around the boundary of the triangle is 0. And this is key because this lets us prove that this lets us construct an antiderivative on any convex set. Or any star-shaped set, but nobody cares about star-shaped sets. So we now just got convex Cauchys for free. Because we know that if we construct an antiderivative, then all integrals are path independent by the fundamental theorem of calculus. We've constructed an antiderivative, and so it is path independent. Yay. This is really, really useful. Another important thing to observe is we know that integration of 1 over z, we know that integration, there's a hole in the set, doesn't necessarily give us 0. So it was very important in that theorem that our function was defined to every point. Can anyone suggest where the theorem breaks if it's not? Anyone? Yes?
Is it that you're not guaranteed a point inside all of the nested sets?
Yeah, exactly. Or rather, kind of that point might be the point where the function breaks. And indeed, if you like run this proof through the integral of 1 over z on a triangle around the origin, that is exactly what you find. Because the integral on every triangle apart from the one containing the origin is 0. And, you know, this is great. This is a sign that we're on the right track. So, okay. So we've just proved convex Cauchy's. Now, let's prove Cauchy's integral form. So, Cauchy's... get my time. This is great, so I'm going to get about halfway through this talk, so I can do a second talk another time. Thank you, Ben. So, yeah, so the same like Cauchy's integral formula is that f of a is 1 over 2 pi times the integral of f of z over z minus a, where this is like a circle that contains a. So, I assume you've all seen this result before, and I think you've all seen the proof of this result. I think this is like possibly the most important result in this entire course, and the proof is quite magic. So I'm going to do my best to demystify it, but it does still require just kind of having a clever idea. So the first thing we need for this to be true is that gamma is like a circle, and a is like a point inside that circle, and a can be any point in this circle. So the first result is that this is true. The first result we need to show is that this is true. And the way we show this is just by saying, okay, so a is smaller than z. So I can write this as 1 over z plus a over z squared plus a squared over z cubed, blah, blah, blah. I'm just expanding, I'm treating 1 over z as a constant, I'm expanding 1 over 1 minus a over z as a power series. So now what I really want to do is to swap the integral and summation signs. Leave the imaginary summation sign here because I'm lazy. So this should in general set alarm bells ringing, but it's all right here because as we know from analysis too, if you have a uniformly convergent sequence, meaning the rate at which these terms add up to the limit doesn't actually depend on what z is, we're allowed to switch the order of integration summation. And because it's a power series, it's quite easy to show that that must hold, because if a is, say, like distance 0.9 from the origin, then you can just bound everything else by like a geometric series. So we're allowed to swap things, and now we just apply the glorious lemma from before. A is a constant, everything which is z to something other than 1 has an antiderivative, so it's 0. So all we're left with is 2 pi I. And everything we did is like completely rigorous. You can do this for yourself if you can. Yes?
Doesn't this follow from just deforming your curve?
Yes.
Like it's integrating 1 over z over L.
But I haven't proven I'm allowed to do that. And I'm being a good boy and being rigorous about things. But yes, like, hopefully it's be kind of clear that this is true, because like you've all seen the residue theorem, you've possibly done convex analysis sheet 3. No, sheet 2 is more with integrals. And yeah, like, you know how this kind of thing works. So this is actually really cool. Yes?
How do you know the power series convergence?
I explained that. You know that, so you can bound each term by like the absolute value of a over z to a power. That is strictly less than 1. And so you can bound the sides of each term by like a geometric series. And we know that geometric series converge. And the rate at which they converge doesn't depend on z, because you know the absolute value of z. So you can show it's uniformly convergent. But like, I'm not going to go into details because I don't think that's a good use of anyone's time. Okay. So let's think about what the statement is actually telling us. You can kind of think of this as like, okay, so intuitively, the only point which matters to find out what the integral of 1 over z minus a is, what does this function look like at the whole? Because we know that we can intuitively, we know that we can deform the path, and as long as we don't cross the whole, it doesn't change the value of the integral. So the only thing which affects the value of this derivative is its value like arbitrarily close to a, and intuitively this is kind of behaving like a delta function should. Like, all that matters is what this looks like basically at a. It doesn't matter if this is like 1 at a and then like blows up really far away. As long as it's still a holomorphic function, all that matters is what it looks like at a. So what I want to do is identify what f of a is. And because all that matters is what this function looks like at a, it should be the same integral whether we put f of a in there or f of z in there, because they look the same at a. So we kind of want this to be true. And that's a best explanation for why this proof is not complete magic. So hopefully that made some kind of intuitive sense to people. Like, if you just think of 1 over z minus a as delta of a, this might feel a lot more intuitive. And if you're the kind of person who like vector calculus, you can think of 1 over z minus a as an irrotational function whose curl is 0 everywhere apart from at a, where it's the delta function. But I don't like vector calculus, I'm not going to talk about that. So now let's do this properly, rather than intuitively. So, kind of, as always, we want to show that the integral of two things is the same. It's much easier to show the integral of the difference is 0. So we want to show that this, just to check, is it kind of, hopefully it's clear that this is exactly what we want, because this is a constant, we just put that out, and we get 2 pi I times f of a. So we want the integral of this function. This is holomorphic everywhere, apart from at a. And at a, we can define this to be equal to f prime of a. Like, the statement that f is holomorphic is kind of literally giving us that this has a well-defined limit as it approaches a. And we'll later see that if we have a function that's holomorphic everywhere but a point, and it's continuous at that point, it's holomorphic there. We can't assume that here, but if we look back to our proof of Cauchy's theorem for triangles, if our function is continuous but not holomorphic at a single point, the theorem still holds. Because when I kind of divide it into triangles, by like the theorem for stuff without holes in it, every triangle but the one with like the weird point in it is 0, no matter how small the triangles get. But the integral around a really small triangle of a continuous function is small. So we can kind of gloss over the fact that we don't know if this is holomorphic at a. Cauchy's theorem still holds. So our proof of convex Cauchy still holds, which means that the integral of this around a closed curve, gamma, is still going to be 0. So we're done. Any questions? Cool. So yeah, this is like an amazingly cool and deep result. And basically everything else cool in convex analysis comes from this. But I think it's worth stressing why this result is cool. It's not that this tells us that the data I have of my function on this curve determines everything inside. We kind of intuitively knew that because of our intuitive picture of knowing the function on a line, telling us the function around that line. The really cool and deep part of this theorem is that it doesn't just tell us that if we know f of z on the curve, we know f inside. It tells us exactly what that is in a really beautiful and lovely form that we can systematically change. So it's not just a result, it's a tool, and we can use this tool to determine future cool results. So let's do this. Cool. I will plausibly run over slightly. Hopefully that's cool, people. I won't be offended if you leave. So in general, in convex analysis, we have two important things with a statement like this. We have the point A, and we have the curve gamma. And we can, whenever we have a statement like this, we want to explore and see what happens. It is worthwhile to vary A, and it is also it's worthwhile to vary A and fix gamma, and it's worthwhile to fix A and vary gamma. So, first off, what happens if we fix A and vary gamma? The most sensible thing to do would be to take a gamma which is just a circle of centre A, and that gives us the max modulus principle, which tells us that... Sorry, is that clear to people, or would people like to see a rough proof? Raise your hand if you want to see that. Cool. Okay, so the max modulus principle tells us that the absolute value of f of A is less than equal to the maximum value of, like, f of z on, like, the image of a circle around, like the kind of boundary of a circle centered around A. You might have seen this as telling you that f of A is at most the maximum on, like, this entire disk, but this is a strong statement and it's also true, so we can prove that instead, because the maximum on a, like, circumference is at least the maximum inside the disk. And this kind of just trivially follows. So we have a circle of center A, gamma of radius r, gamma is the curve round. We know from Cauchy's integral formula, so CAF implies that f of A equals 1 over 2 pi I times the integral around gamma of f of z minus A. But absolute value signs around, and this is at most 1 over 2 pi times len that, no, all around. Yeah, this is at most the length of the curve times, like, the maximum value of z on this thing divided by z minus A. But because we chose gamma so nicely, so that the radius was fixed, this is just r. And this is constant, we can pull it out. And the length is just 2 pi r. And, oh look, done. So, like, this is like a cool and useful statement, but I don't think this is a deep statement. The deep statement is Cauchy's integral formula. This is just kind of an easy consequence of that. And, so, in general, varying gamma isn't that interesting. We care about functions and how functions vary. And so it's a lot more interesting to fix gamma and vary A. So we're going to get two really cool results from this. The first is kind of a much more basic result, Liouville's theorem. So Liouville's theorem says, I don't know. So Liouville's theorem says bounded implies constant if f is defined on the entire complex plane. So let's think about why this is true. So we know Cauchy's integral formula tells us that the value of the value on some circle determines every point inside. We've got the freedom to choose the entire complex plane, so let's pick a really big circle. And let's just look at two fixed points in the middle, say 0 and 1. Cauchy's integral formula tells us that f of 0 is the integral around gamma of f of z over z. F of 1 is the...
Do we need the 2 pi I?
Sorry? Yeah. So the important thing here is basically just... So f of z on the boundary is kind of fixed and bounded. You can think these as like boundary conditions that determine our function inside as like some kind of solution to a differential equation, if you're in applied mode. Don't do that. So, and now let's just, so we want to show two things are the same, which is what it means to be constant. As always, take the difference. So the difference between these two things is like 1 over some crap divided by f of plus or minus, kind of which one goes. And so now we're just done. So this is a bounded thing above a quadratic thing. The integral contributes a linear factor that is length. So in total, this is like 1 over the radius asymptotically. So you just pick a really big circle, and this goes to 0. But this is fixed. It doesn't depend on what the circle is. And so what the statement is, and so, well, we know this can be 0. So what the statement is really telling us is that when we set our boundary conditions to determine the function inside, we need to kind of have a lot of room to do interesting things, otherwise our function's really boring. Cool, so that's Liouville's theorem. I think this is kind of a cool result in and of itself, but also that there's a lot of kind of, it's a lot more powerful result than people first give it credit for. So let's think about why. So let's suppose that, let's suppose you've got a function whose image is not dense in the complex plane. What does that mean? There exists an A such that for all z, the distance of the image, the distance of the output of f from A is at least epsilon. What this means is that 1 over f of z minus A is at most 1 over epsilon. And yeah, but because f of z never goes near A, and because f of z never goes near A, this is always defined. This is a holomorphic function. This is bounded, and so this is constant, and so f is constant. So what we've shown is that every holomorphic function is either constant or its image is dense in the entire complex plane. And this is kind of equivalent to Liouville's theorem. So let's take a fun consequence of this. The first of 3 proofs I have planned of the fundamental theorem of algebra. Also, definitely not going to get the other 2. So we know, so we take a polynomial from C to C. This is holomorphic on the entire complex plane. We know this because polynomials are differentiable. We can prove this really easily. And so the image is dense. But polynomials have the really nice property that as z goes to infinity, they become dominated by the leading term. Like it gets bigger than everything else. And so as z goes to infinity, the output goes to infinity. What does this actually mean? This means that I can pick a really big circle so that the image of the outside of this circle is kind of, say, at least got absolute value at least 1. Like, this is my input plane, this is my output plane. I take the unit circle, like all this stuff maps to like only this stuff. But I know that the image of this polynomial is dense. So the image of this like disk, notable for being closed and bounded, and so compact, fills in this gap because it's dense. So the image of this closed and bounded disk gets arbitrarily close to 0. But this is compact, and as we know from Mess and Top, the continuous functions map compact sets to compact sets. So the image of the disk is closed and bounded, and it gets really close to 0, which means it contains 0, because that's what being closed means. So the fundamental theorem of algebra is just kind of like a consequence of this much stronger result that the image of entire functions are dense in the complex plane. Does that make sense? Yeah, and so, yeah, and kind of as you may have seen on example sheet 2, the property that, like, as z goes to infinity, the output of our polynomial goes to infinity. So the output of our function goes to infinity actually exactly characterizes what it means to be a polynomial. So sadly this proof doesn't work with those. But this also has the really cool consequence that polynomials are surjective, because there's nothing special about 0. Like, it has nice properties if you think about polynomials, but if I just subtract a constant from my polynomial, that new thing having a root is the same as the original polynomial having that in its image. And so what I've basically just shown is that polynomials are surjective. Or to take a kind of flip this image around, in order to like have a 0 not be in their image, the polynomial must kind of each closed disk that I draw can't get too close to 0, otherwise it would contain it. Sorry, the image of each closed disk is closed, and so it can't get too close to 0, otherwise it would contain it. So as I draw like a sequence of bigger and bigger disks, their images must get closer and closer to 0 because the image is dense, but doesn't contain it. And that requires arbitrarily far out points to be arbitrarily close to 0, which means that the image really far away must get arbitrarily close to 0. Which means that the image really far away can't be like really far away from 0. And that's kind of another way of saying this is true. Like, if you, in order to not have a point in your image, that like strongly constrains how your function can behave as it goes off to infinity. Hopefully that makes sense, people. Let's move on, because time. So, now I'm going to prove what is possibly the second most important result.
Get that extension called
Power series. Or the statement that
1%.
every holomorphic function is equal to its power series within the radius of convergence. Sorry, within a non-trivial radius of convergence. So, this is kind of a pretty trivial consequence of Cauchy's integral form. Because if you look up here again, if we think of the values of f on this circle as just like fixed boundary conditions, this is a really, really nice thing. This doesn't just tell us we know f of a, it tells us that we systematically know f of a, and we know how it varies. So, like, let's just apply the same trick we used to calculate the integral of 1 over z minus a to calculate this integral. So, this is, again, expanding its power series. So, we know, again by mess and top, that because gamma is a circle, and circles are compact, and f is a continuous function, the absolute value of f is bounded on that circle. So, the same proof that this power series is uniformly convergent still applies. Like, there's an f of z here now, but that thing is bounded, so it doesn't affect the fact that our convergence is uniform. I'm not going to formally do this because I'm running out of time. I don't think it's that interesting. But we can again show that this is a uniformly convergent series. And so we can again swap like the order of summation and integration. So like, yay, integral signs. And sadly I don't get the result that kind of everything but the first thing is 0. But I do get the result that I can just move a outside. And now, like, these depend on what my function f is, and they depend on what my circle is. But if I fixed my circle, it doesn't matter. Like, these are just constants as I vary a. And so, I now have a power series. Yep. Terrible notation, sorry. Yeah, I now have a power series. There are these coefficients, which have this funky form, and the exact form isn't that important. The important fact is that, like, this is a power series. And much more importantly, it is not only a power series, it is a power series that converges. And we're not going to apply any of the random tests we learned in analysis 1 or anything like that to show that this converges. We know that it converges because this is the value of f of a. This is an actual value. This is finite. This exists. This is defined. And we've shown that this integral is equal to this sum. So the sum is equal to a thing we have defined. Sorry, the sum is equal to a thing we know exists, and so it must converge. And so we kind of get for free that the radius of convergence of this series is at least the radius of our circle. And like, this is amazingly powerful and amazingly useful. Like, there's 2 exclamation points in my notes. And this is, so first off, this is not true in the real case. Like, if I have e to the 1 over x squared, the power series when I expand around 0 is just 0 everywhere, but the function isn't 0, like, anywhere apart from the origin. where you define this to be 0 at x equals 0. Because kind of, as x gets really small, this gets really big, but it's negative, so this goes trends to 0. And so, like, this is a lot more powerful than it is in the real case. So, I think it's worth stressing why it's so exciting that we've shown that it is a power series. So, power series are kind of, you can think of it as the completion of polynomials. Like, you can define the partial sum up to the nth point, up to the like kth point, as a degree k polynomial. And within the radius of convergence, this is a uniform limit of those polynomials. And polynomials are really, really nice. And uniform limits don't preserve everything, but they preserve lots of nice properties. And so you can kind of get a lot of really lovely properties using the fact that is the uniform limit of nice things. So, to take one example, I think it's also worth stressing that, again, this isn't just a result, this is a tool. Like, we now know that we can write any holomorphic function in this form. And as I hope you know from like studying maths, when we're able to write something in this lovely form, we can do lots of powerful things with it. Like, we can think about how limits work. We can think about the local behavior. So let's actually apply this and see what cool stuff we can get. So, first off, get rid of this. Just write the key results that f of z is a power series. So, first off, we get the principle of isolated zeros. This just tells us that, okay, if this function is not 0 everywhere, there's a non-zero coefficient in this power series. We look at the first one, that's like bk times z to the k times 1 plus some stuff. In general, like, when I take my power series and I transform it to another power series like this, and I'm just doing simple things like translating the coefficients, dividing through, don't stress about things like radius of convergence, because this will almost always preserve those. And proving that is kind of always going to be really easy. So what I've just done is I've taken my power series, I've transformed the coefficients to a different power series. It's got the same radius of convergence, and it's quite easy to show that all power series are differentiable. So this is holomorphic, and so this is just like a polynomial times a holomorphic function, which is evaluated as which evaluates at 0 to 1. This is continuous, so locally, this just looks like so kind of very close to 0. G is not 0. This is not 0, this is not 0, and so the entire thing is not 0. So from this you get the principle of isolated zeros, which tells us that, like, given any point, A, there is a radius such that f is non-zero on, like, this disk, on the function disk. And that just follows from this. Observe that it didn't actually matter whether f had a root at 0, and it also didn't matter that I chose 0 as the source of my power series, because I can just translate my function. So I would henceforth just always take 0 as the source of my power series. The reason it didn't matter if it was 0 is that if k is 0, everything I said is still true. Like, z to the 0 is not equal to 0 close to 0 because it's 1. And this power series is well defined and holomorphic because it's the same power series. So, and this is an amazingly cool result because it tells us that if we ever have, like, a 0, we can draw a disk around it, and there are no other zeros inside this. Again, the way to tell if two things are the same, if you know they agree on like some points, is that the difference, you know the difference is 0 on the point where they agreed. Does this supposed to be 0 everywhere else? this result is telling me that two different holomorphic functions can only agree on an isolated set. And this is incredibly powerful, because it tells us that if I have like a sequence tending to a point, or a line, or like a tiny disk, or anything like that, if I know what my function is, if I know two functions agree on this, they agree everywhere. Which can be rephrased as, if I know the function on like some tiny countable set like this, I know the function everywhere. So the final bit I want to talk about is the other really important consequence of the fact that we've written as a power series. So it is a true statement from analysis 2 that if you have a power series, it is infinitely differentiable inside the radius of convergence. There is, you've probably seen 3 proofs of this. There's a really nice one involving integration uniform convergence. But did you see that in analysis 2? Well, that's depressing. Look at, I don't have time. I might go through the first one and ask questions about it. So, okay, so fact. Power series are infinitely differentiable. So we know that holomorphic functions are power series, and we also know that power series are holomorphic functions. So this is telling us that if a function is first differentiable, it is infinitely differentiable. So this is really useful, and hopefully it's obvious this is really useful, but I think it's kind of a lot deeper than it seems at first glance. So I kind of want to try and change your perspective or intuition now. So hopefully you have the intuition from real analysis that differentiation makes things rougher, integration makes things smoother. Does that make sense to people? Yeah. Like, integration preserves more things than differentiation preserves. I can have a function which is like once differentiable. If I differentiate it, I lose that. But if I integrate a once differentiable function, it's still once differentiable. It's actually twice differentiable, which is even stronger. So like integration kind of creates niceness, differentiation removes niceness. But that perspective is just completely false in the complex case. Because everything is infinitely differentiable. Like, in the real case, differentiation as like an operation moves me from like n times differentiable functions to n minus 1 times differentiable functions. Like, I'm losing information. But this asymmetry is not there in the complex case. I keep going between like smooth things and smooth things. Or, to take another way of thinking about this, if I have a power series and I differentiate, I just like shift all terms to the left and multiply each term by a constant. Or if I integrate, I shift everything to the right. And this will lose me like a finite number of terms at the beginning, but it will keep kind of the infinite structure the same. And translation, it kind of is a symmetric operation. So it is kind of, they are kind of dual operations in some sense. Or to take another way to see that this is true, by how I prove there are power series, I also got a formula for what the derivative looks like. There might be a negative sign in here, I don't know. And because like the coefficients of the power series are also the derivatives. And so this is a really cool and deep result, much deeper than it seems at first glance, because what it's telling me is that if I want to differentiate a function, I can do this by integrating. And so they kind of are fundamentally symmetric operations. So let's do some quick examples to kind of make it clear that they are like much more symmetric in complex analysis than they are in real analysis. So one good example of this lack of symmetry in real analysis is that if we've got a sequence of functions that like uniformly converge to f, it is not the case that their derivatives uniformly converge to the derivative of f. It's not even necessarily true that f is differentiable at all. For example, if f n of t is 1 over nt times sine of n cubed t cubed, I think should work. Like, you've got some sine waves of like massively increasing amplitude, massively increasing frequency but decreasing amplitude. The amplitude tells you the value, which limits to 0, while the frequency doesn't tell you anything about the amplitude, but it tells you about the derivative. So, like, differentiation has lost information. But this is not the case in complex numbers. If f of n limits to f uniformly, and they're both holomorphic, then I can, like, take an integral of this. I can just look at a small disk, so it's convex, I'm allowed to take antiderivatives. So I now have a sequence of antiderivatives. And I know that integration preserves uniform convergence, because, like, you prove that analysis too. So this means that this uniformly limits to the antiderivative of f. And further, these are both power series. And if power series uniformly limit to each other, the coefficients must uniformly limit to the coefficients. I'm not going to prove that, but, like, that's not hard to prove. And so, and if you have got two power series which agree, then their derivatives also agree, and their derivatives are uniform limits of each other. And so, like, but more importantly, their second derivatives uniformly limit each other and agree, and their second derivatives exist. So we have the result we wanted. F is the derivative of a holomorphic thing, so it's infinitely differentiable, and its derivative is the limit of these because everything is a power series, and power series are nice. So our intuition from the real case is just completely wrong here. Differentiation preserves as much interface as integration preserves, because they're, like, fundamentally symmetric operations. Or, to take another quick example, if you will forgive me for everyone like that, Morera's theorem. So, Morera's theorem states that if, like, the integral of f is path independent, sometimes phrased as the integral around any. Well, thank you very much for coming. If the integral around any closed curve is 0, or if the integral is independent of exactly what the path is, as long as you know the endpoints, then f is holomorphic. And f continuous. Then f is holomorphic. And the reason this is true is path independence lets us construct an antiderivative. Like, that's the entire point. So f has an antiderivative. The antiderivative has a derivative. This is the point. It's holomorphic. And if you're once differentiable, you are infinitely differentiable, which means your derivative is infinitely differentiable, which means f is holomorphic. And that might seem a little bit like magic, but hopefully if I phrase it like this, it's a bit clearer. Like, f has antiderivative is equivalent to f times derivative. The statement f has an antiderivative is just saying the integral is path independent. The integral is path independent tells us it's holomorphic, because we know if it's once differentiable, it's infinitely differentiable. And kind of, if you know that it's differentiable, then we can apply Cauchy's theorem on, like, a small disk to construct an antiderivative. And hopefully this kind of makes it a bit clearer what I was saying about how they're fundamentally deep and symmetric operations. So that is the end of the first 6 minutes of my talk. I'm not going to try and get the rest, but let's just try and recap what we've just done. So we tried to prove, we first wanted to ignore the path independence issue and just have a single canonical path to look at, a line. This meant we had to look at convex sets, which was fine, but we wanted to look, and in order for the result to be true, we needed to be true for triangles. And the way we proved this is we said, okay, so being differentiable is like saying you're locally linear. Being locally linear is like saying you're locally got an antiderivative, which means that on a really small integral, the integral is approximately 0. And the entire rest of the proof is just finding clever ways to formalize this intuition. Cauchy's integral formula is kind of a semi-magic trick, which comes from this one clever idea of looking at f of z minus f of a divided by z minus a, which is really just saying 1 over z minus a behaves like a delta function. So if you have two things that look the same at a, the integral looks the same no matter where the integral is being taken. And this is a really deep result, because I can vary the curve and fix a, or I can vary a and fix the curve. And and it gives me a tool to systematically predict how things will happen. And then this gives me loads of key results. Like there's something Liouville's theorem by kind of simply varying A, and this tells me that the image of any entire function is dense. And being more systematic about how I vary A, I get a power series, which is an incredibly valuable tool, because it tells me both that the roots of a function must be isolated unless it is 0, which gives me the core idea of analytic continuity, and it tells me that being differentiable once is being infinitely differentiable, which tells me that differentiation and integration are like symmetric and dual operations here, completely unlike in real analysis. And that seems like a good ending point.